Okay, one more problem I want to do today. So we have this differential equation, y prime is equal to y minus 1 times y minus 2. Now, what makes this guy special, if you look at him, everybody's a y. There are no x's or t's. Y prime here is simply a function of only y. We don't even know what the independent variable here. Oh, yeah, we do. It's right there. It's x. But there are no x's in the equation. We call these autonomous equations because y only depends on itself. Auto means self. Autonomous DEs, we even without solving them, we can kind of get an idea what the solutions must look like. Because if dy dx equals 0, that means the function's not changing. That means if the derivative of something is 0 at some particular value, that means you would get a constant. And that would be a constant solution. Remember, differential equations have an infinite number of solutions. The constant solutions here are the ones that make this 0. So if we had y minus 1, I'm setting the right side equal to 0. That's already in factored form. We can just see we get y equals 1 and y equals 2. Those satisfy the DE because the derivative, if I take the derivative of 1, I get 0. Both sides of this equation would be 0. Plugging in 1 here makes this 0. Taking his derivative makes this side 0. 0 equals 0. Same thing here. So these are the constant solutions to this autonomous DE. So I could graph those solutions. Here's y equals 1. That's one of the solutions to this DE. Here's another one, y equals 2. Now, what's interesting is we can use the DE to get kind of a feeling for what the other solutions might look like by building a sign chart. So let's build a sign chart. Just like you did back in pre-calc, in college algebra, and so forth. So I've got here my two autonomous constant solutions, 1 and 2. And I'm going to do this the way I would do it in a college algebra class. I'm going to write down my factors over on the side. And then I'm going to use test points for each region here. So I've got 3 regions. So if I plug in any number less than 1, say, for example, I plug in, say, y equals 0. 0 minus 1 would be -1. I'll write it out. That's negative. I don't want to put that there. Negative. What if I plug in 0 here? 0 minus 2 is also negative. A negative times a negative is a positive. Okay, what if I plug in a number in here, say 1.5? 1.5 minus 1, that's 0.5, that's positive. But 1.5 minus 2, that's negative. That would be -0.5. A negative times a positive is a negative. And similarly, if I plug in maybe 3 minus 1 is positive, 3 minus 2 is positive. Positive times a positive is a positive. So what that means is in this region, remember, here's my DE. The derivative of y in this region here, so on the region -infinity up to 1, dy dx is positive. What's that mean? If a derivative is positive, that means y is increasing. That's what it means to have a positive derivative. In this middle section, from 1 to 2, the derivative was negative. If the derivative is negative, then the original function must be decreasing. And similarly, from 2 to infinity, the derivative was positive again. We got that right there, right here. So y must be increasing. So now I can sketch out what these graphs must look like of solutions here. So let me do this in a different color. Maybe we'll use orange. So we're looking vertically here. So normally when we're doing sign charts, we're doing them for x's. Here we're doing them for y's. So what I said was, for any y value less than 1, I have to have an increasing function. So all my functions that live down here must be increasing. So a solution curve might look like this. It's something that's increasing. And here, this might be another solution curve. And I don't know exactly what the shape is going to be. I just know they're increasing. In this region, from 1 to 2, we get decreasing. So my solutions must look like this. They must be coming down. And again, I don't know exactly what they look like, but I know they're coming down. And then here, above 2, we got increasing. So what that means is, if we look at these solutions, any solution near y equals 1 is being attracted toward it. So if I had a solution that, say, passed through this point right here at, say, 1/2, that solution, as x gets bigger and bigger, must be getting closer to the constant y equals 1. Similarly, if I had a solution that passed through this point, it must be getting closer to y equals 1, because these were all decreasing. So we call this guy attractive. And this one is repulsive, because any solution near y equals 2 shoots off away from it. So these two here we call equilibrium solutions. Because they're just flat. And this is a stable equilibrium. Like if you put a ball in a valley and you shove it a little bit, it'll roll back down to this stable equilibrium. An unstable equilibrium is a ball at the top of a hill. If you give it a shove, it'll roll away. It won't come back to equilibrium. So this is a stable equilibrium solution, and this is an unstable equilibrium solution. Okay. And we can actually graph these out. We can actually look at all this using something called a slope field plotter. So there they're calling it f prime, but that's really just y prime. And what was it? It was y minus 1 times y minus 2. So that's what my solution curves will look like. And if I pick any point that I want my solution curve to go through down here below y equals 1, that solution curve will eventually get closer and closer to that stable equilibrium, even if I pick something in between 1 and 2. But if I pick something near y equals 2, but not exactly there, you're not getting closer to that equilibrium, you're running away from it. That's an unstable equilibrium. If I'm right at 2, I'm at equilibrium, but if I'm just a little bit away from it on either side, I run away from it. as x gets bigger. Okay, that's about all we're going to do with autonomous DEs. Like, I didn't even bother making a lecture video about them. I just figured I would cover it here in this homework problem. So don't stress about all this. Like, I've literally covered everything about autonomous DEs and stable and unstable equilibria right there in this video. That's all we're ever going to talk about it.